Hi, welcome back to my lectures on groups, rings, and fields. Our next topic is on group action on a set. Group action on a set. So let us start with an example. Let us take a set like this, x equals triangle ABC, triangle BCA, triangle CAB, triangle ACB, triangle BAC, and triangle CBA. 6 elements. And this is actually a same triangle but in a different orientation. I'm going to take a group. I'm going to take the symmetric group with elements 3. And we know that the elements of the symmetric group is the identity element, the rotation 1 and 2, and the mirror images 2 and 3. So these are the 6 elements of this group. This is a group and this is just a set. There is no binary operations defined on this. So what I'm going to do is I'm going to take one of the group elements, let's say sigma 1, and I want to apply that that element on one of these elements on the arbitrary set. Let's say ABC. I'm going to skip the notation of triangle here. This is triangle ABC, and this is it's a 120 rotation to the clockwise direction. So this will be BCA, another element in X, and sigma 1 of BCA is going to be CAB, sigma 1 of CAB is equal to ABC, sigma 1 of ACB is equal to CBA, sigma 1 of BAC is equal to ACB, and sigma 1 of ACB is equal to CBA. Similarly, I can define a map for sigma 2, mu1, mu2, and mu3, and of course identity is the same. So what I'm doing here is I'm going to create a map from S3 cross X to the Cartesian product of S3. This is the group and this is an arbitrary set to itself, to the same set. So here what I'm going to do is here I'm going to take an action, a group action on this set and getting here. And that's exactly what I'm doing here. And you can define exactly like this. So here the property of this map is that this is a group and this is an arbitrary set, and this is a set. So there is an identity element here that when you operate on any x, that should go to the same x, and that's exactly what's going to happen here also. I didn't write it down, but that's what's happening there. So let us write it as ex, action of E on x equal to x. And if you take two elements from here, let's say G1 and G2, or here in this case it's going to be sigma 1 times sigma mu1. Let me take it as G1 and G2. So G1 and G2, G1 times G2 is again an element in S3 or a group. Of x will be mapped to G1 of G2 of x, or you can say G1 of G2x. G2x is again an element in x, so G1 acted on that element, and that condition is true here. So that kind of map is called a group action. On a set x, or you can say x is a G set, where G is the group. So that is a definition of the group action. So let us write down the formal definition of an action, a group action on a set. Let X be a set and G be a group. Then a group action of G on X is a map defined as follows. It's from G cross X to X with the following properties. Ex is mapped to X for all X in X, and E being the identity of G. Second property, G1, G2 of X is mapped to G1 of G2X. For all G1, G2 in G and X in X. So then we say that X is a G set. So let us take an example. Let X be any set. Then XX be the group of all permutations on X, and let H be a subgroup of Sx, just like we did when we started this topic. So this Sx is our this is not generated from X, but I'm saying this is more like that. Instead of Sx we used S3. Subgroup, then H is X is an H set with the action as follows. We need to define the action. So what is action here? It has to be from X to X. What is X? What is in H? Permutations. So these permutations are on X. Something like this. Let us say X equal to 1, 2, 3. Then Sx will be our normal E sigma 1, sigma 2, mu 1, mu 2 and mu 3. Okay. So this is going to be, let us say, probably sigma 1 will be, you will write it as 1, 2, 3, 2, 3, 1, something like that. This is the permutation. So this will be, this is going to be defined by sigma of X. Sigma acted on X is going to be sigma X. Meaning, if sigma 1 is an element from Sx and 1 is an element from X, then it is going to be sigma 1 of 1, and that is equal to 2. And that again belongs to X. And that's what I'm saying here. Then this map is an action, is a group action, is a group action on the set X. In order for us to prove this, what are the things we need to do that? The identity element of H is the identity permutation. So E of X always goes to X. Clear? No problem. And if you take two elements from here, let us take H1 and H2 belongs to H, then H1, H2 of X is equal to H1 of H2X because the permutations are composable. So this is our first example. So what you have done is given a set and the group of permutations on X, we created a action, group action. And we defined a G set, a G set. Now, if a G set is given, then we are going to derive permutations from the G set. So, let X be a G set. Start with a G set. The previous example, we started with an X and a group of permutations and created a group action. Now we are given a G set. Then define or for a G in G, define sigma G from X to X by, see, we are given a G set, meaning there is a function already given from G cross X to X, meaning for every G and for every X there is an element defined here that is given. Now we are going to define a map from X to X by, for given a G in G, sigma G of X, because it's a map from X to X, is equal to Gx. This is well defined because we are given the G set. So if this is defined like this, then G sigma G is a permutation on X, and there exists a homomorphism phi from G to Sx. Sx is the group of all permutation on X. G is our group. Okay, so by phi of G is equal to, this should be, we are mapping from group to a group of permutations, so this has to be a permutation, and that is sigma G, defined as this. Okay, so there are two things to prove here. We need to show that sigma G is a permutation, and we need to show that this is a well-defined homomorphism from G to Sx. So let us prove this one. To show that sigma G is a permutation, we need to show that sigma G is a map from X to X, show that is a onto and 1 1. If we can show that this is a bijective map, then it is a permutation. So sigma G of x1 is equal to sigma G of x2. That is how we normally show it's 1 1, right? That implies gx1 is equal to gx2. And that implies G inverse of gx1 is equal to G inverse of gx2. And that implies x1 is equal to x2. Implies sigma g is 1, 1. It is onto because for every x in X, G inverse of Gx is equal to X. Or it is other way, G of G inverse. So for every x, there is an element here that when acted upon G will give you X. And that implies sigma G is onto. Implies sigma G is a permutation. To show that phi is a homomorphism, phi is a function from G to Sx. So if you want to show it's a homomorphism, we need to show that for G1, G2 in G, phi of G1, G2 is equal to phi of G1 times phi of G2. Phi of G1 times G2 is an element in Sx. So this is a permutation and this is also a permutation, and this is actually composing. Okay, so if you want to show this permutation is equal to this permutation, what we need to do is, these are permutations on X. So if you want to show that these two permutations are equal, what we need to do is take any arbitrary element from X and find out the value of that X on this permutation and see that they are equal. So for X belongs to X, phi of G1, G2 of X equal to, by definition, it is actually phi of sigma of G1, G2 of X, and that is equal to G1, G2 of X. And that is equal to G1 of phi of G2 of X, and that is equal to phi of G1 operated on phi of G2 of X. And this is true for all X in X, and that implies phi is a homomorphism. So what we have found is that if X is a G set, then there exists a homomorphism from G to the group of all permutation on X defined by phi of G is equal to sigma G, which is defined as sigma G of X equal to Gx. Now, this is a homomorphism. So, what is the kernel of this? The kernel of phi is a subgroup of a normal subgroup of G. So, it's coming from G such that phi of G is equal to the identity permutation. What does that mean? That means the subgroup of all elements in G that fixes X under the group action. So let us call this as N, and it is a normal subgroup. Then N is a normal subgroup. So factor group exists. Now let us see, we can define a map from the factor group of X to X. So we are going to create a G power N set by Ng operator on X is equal to Gx. Then X is a Gn set. We still have to prove that this is a G set. In order to prove that this is a G set, we need to prove that for all E in Na, in not Na, in Gn, Ex is equal to X. And if you take two elements, what are the two elements like G1, G2 in G over N, then Ng1 after Ng2 of X is equal to Ng1 of Ng2 of X. I'm going to give this one as an exercise. Now, this homomorphism, if kernel of phi is equal to just the identity permutation on Sx, and that implies phi is 1, 1. In that case, we call the action, the group action, to be faithful. Another definition. And one more definition before we move forward. Let X be a G set, then for x1 comma x2 belongs to X, if there exists a G in G such that x2 is equal to x1 x, gx1, then the action is called transitive. The group action is called transitive. Meaning you can reach any element. If you take any element here, any two elements from here, we can find a element in G so that one is the action of the group action of the other. Two elements here, x1, x2 in X, we can find a G in G such that you can reach x2 by operating G on x1. Then it is called transitive.